Hola, chaps. Let's learn.
Hola, chaps. Mr. Turek here. For physics, I wanted to explain a little bit about the polarization of light. So, in December 1971, science writer Isaac Asimov published an article called Seeing Double. And I remember reading it, and I can remember vaguely the story behind it, but I can't find the details on this story right now because it's not publicly available. But the story went something like this. Once upon a time, there was a farmer, and in the spring, he was clearing his field of the rocks that come up during winter out of the ground. And he held up a rock, and it was sort of a crystal type rock. And as he held it up, he could see through it. And as he rotated it, it formed a double image. And he found that was amazing. He took it to the local university, and they examined the rock, and they had never seen anything like that before. So at the time, people tried to come up with an explanation. How can there possibly be two images when you look through this particular crystal? They didn't figure it out. A number of outlandish, for the time, ideas were put forward, and it became just a scientific curiosity of the time. And so you could go to the local science oriented gift shop and get yourself a little sample of this crystal as a souvenir of your interest in science, just a curio to have in your home. So a kid had one of those in his possession, and he got accepted into college. And as he moved into his dorm room, it was a sunny day. This was at, I believe, in Paris, and he noticed that there was light reflecting off of another building across campus. One of the windows was angled just right, and the sunlight was reflecting off of that distant window into his own dorm room. And he happened to have that little crystal with him, and he held it up, and when he rotated it, the reflected light that he saw disappeared. And so, just like that, before even starting the first day of classes in college, this kid made a scientific discovery that no one had ever made before. So, there's no telling what you might do when you go to college, but things can happen unexpectedly. And so, he discovered it and reported it, and it led to scientific investigation that realized that there really are two kinds of light. And when you look at the light coming from the sun or something like that, you don't realize it. So I'm going to try to explain it to you a little bit and demonstrate it for you. So there are transverse waves and there are longitudinal waves. A transverse wave is something that I could represent by drawing a sine curve, something I can't draw very well, but it means that the direction of vibration is perpendicular to the direction that the wave moves. So this represents a wave that is moving, let's say, off to the right, but the particles that make up this wave are vibrating, let's say, up and down or side to side, perpendicular to the right. We demonstrated this in class with you students trying to do the wave one day. And one student tried to stand up, and then the student next to them, and then the student next to them, and it didn't work very well in your period. But the concept was you students stood up and sat down, but the wave itself went left to right across the classroom, or right to left from your point of view. So that is a property of a transverse wave. But when we draw this sine wave, it can have two perpendicular components to it. And light waves actually have these two perpendicular components. One of the components is an electric field, and let's say that it goes up and down vertically. The other component is a magnetic field, and relative to the electric field, it goes perpendicular to it. Now, I can't draw perpendicular, so I shouldn't even try. But imagine that I have a sine wave still, but now it's going side to side, whereas the electric field is going up and down. So those are the two components of a light wave. And some physicists, James Clerk Maxwell comes to mind, came to the realization that a changing electric field creates a magnetic field, a changing magnetic field creates an electric field. And so a ray of light, a photon of light energy, is a changing electric field. It creates a changing magnetic field. It creates a changing electric field. And all this goes on for a wave train that's about 2 or 3 meters in length. And that's one quantum of energy going through space. Now, what does this have to do with the kid and the funny crystal? Well, as it turns out, that one kind of electric field can reflect off of a surface and the other type can't reflect off the surface for a particular orientation. And there's certain angles, like a Brewster angle comes to mind, where you have to do this to get it to work just right. But in general, for me trying to, briefly explain this concept to you, imagine if I were to take some volunteer students in our classroom and have them come up to the front of the room, and then I would hand each pair of students, so I have 2 pairs of students, a set of 2 boards, so 1 board for each student. And I set up a slinky between myself and some other students. Ratika comes to mind. So Ratika's there, I'm here. And we take a slinky and we set up a standing wave between the 2 of us going up and down across the classroom. And then on either side of the slinky is a student. And there's one student on one side, one student on the other. And each student is holding a board. And each board is parallel to this motion of the slinky. So for your imagination, let's say the slinky is going up and down vertically from ceiling to floor, while Ritika and I are standing on opposite sides of the classroom. And on one side of the slinky is a student A, and the other side is student B, and they're each holding a board vertically. And they're holding them pretty close to each other, but there's just enough room so that the slinky can go up and down. What would happen? Nothing. The slinky would go up and down between these 2 boards that are next to it, but not touching it, and there's nothing going on. Now, what if I were to bring 2 more student volunteers up from the classroom? And this is what I normally do when I teach this part of the course. You're just missing out on it because you're home and I'm home. But I would normally bring up student C and student D and give each one of them a board as well, and have them stand next to the 2 students A and B. So now we have 4 students plus Ratika and me all up in the front of the classroom. Ratika and I are still vibrating the slinky up and down vertically. Students A and B are still holding 2 boards parallel vertical with the slinky between them, having no effect. Now I have students C and D do the same thing, standing next to students A and B, parallel to them, down the length of the slinky a little bit, let's say towards Ratika, and they're also holding their boards parallel and vertical. What happens? Nothing. The slinky goes up and down between 4 boards now instead of 2 boards. Ah, but what would happen if I had students C and students D now rotate their boards by 90 degrees so that instead of being vertical, they're now horizontal? And if this pen represents the direction that the slinky is going, then originally it went like this, and now the pen is sandwiched between 2 horizontal boards at the same time that it's sandwiched between the 2 vertical boards of students A and B. Now, what happens? Well, if we did this demonstration, what you would see occurring is that the slinky would work fine until it got to those 2 horizontal boards. But now, when it wants to go up, the board blocks it. When it wants to go down, the board blocks it, and the slinky wave stops traveling at that point. So the slinky stops going up and down, the wave is stopped. In real life, light coming from the sun is unpolarized. That means the orientation of the light waves is in all random directions. So it's not just horizontal, it's not just vertical, it's any arbitrary angle whatsoever. One might be the electric field, and then perpendicular to that is the magnetic field, and they go off through space from the sun to the earth. What I can do conceptually is take something like a piece of glass and then put some really, really small gratings on it, sort of like long, thin boards, but they have to be on the size of the wavelength of light. Now, light is many times smaller than the diameter of a human hair. So this isn't something that I can do easily, but it is something that we can do chemically. We can take a long chain polymer and then stretch that long chain polymer across a piece of glass. When we do that, we create a polarizer. And so here's a piece of glass, and it has that long chain polarizer stretched across it. And what I'm claiming is that it's like a pair of boards that only allow one orientation of the light to go through it. So when I hold it up in front of this computer monitor, and I don't think I'm going to be able to zoom in for you on this one, but when I hold it up in front of this computer monitor, you can kind of tell that it's blocking the light pretty well. That maybe you can see a little bit through it. I mean, I can make it out on my screen. I suppose if I bring this closer to the camera, you could see that you are actually looking through it, right? Okay, it's dirty, yeah, I know. Well, I can clean it up well enough for you. So here's a polarizer, and when I rotate it, look what happens. The light, now you can see through it. Before, oh, now it's black. So I'm going to bring this close to your screen so you can see it in more real time. I rotate it one way, and you can see through it, the screen. I rotate it the other way, and the screen now goes dark. Rotate. It's hard for me to do this clearly, right? And dark. So what magic am I doing? Am I turning the screen on and off? No, look, both hands, I'm not using my foot, I'm not using my hands. So what's going on is the light coming out of the monitor is polarized already. And so imagine, just for argument, that it's already vertically polarized, and this polarizer now acts as an analyzer. So when you have a second polarizer, that's called the analyzer. And when the two line up in the same direction, which would be like this, now the light can pass through. And when I rotate it 90 degrees, now it's like the crossed boards, the light is blocked. I have a second polarizer, right? So I can demonstrate the same with this other guy. You can see he's got his polarization working as well. Let's put him up by the camera. Oh, he's much cleaner than the other guy. Nice to see. So when I rotate it, of course I can't control it very well. Let me try rotating it and controlling it, and you can vaguely see that it works. So one thing that would work really well is if I set this one so it passes through, and I set this one so that it passes through. So what do you suppose will happen when I put one in front of the other? Well, light passes through. And now when I cross one with respect to the other, just rotate it. Oh, there you go. It's blocking the light. It's polarized. So one of these is lined up with the polarization of the monitor, and the other one is now crossed to it. When they're crossed, it blocks the light. When they're both lined up with it, it lets the light through. I'm going to bring both of these up to your computer screen. Let's see, I'm going to go like this because it's a whole lot easier to hold it. Bring it up to your computer camera, and now I'm going to rotate 190 degrees. And what you can see is it's blocking all the light now, not just light from the monitor. And it's not perfectly blocking it, that's true. That has to do with the extinction ratio of the quality of the polarizers and the capabilities and limitations of the technology being used. However, it's still doing the job. It is letting polarized light through, and when I rotate it 90 degrees, it's crossing it down. In fact, you can make me kind of disappear, interestingly enough. There you go. Life is interesting. So uncrossed or aligned, and crossed, blocking it, blocking not just the monitor, but all the light coming from behind it. Okay. One of these is crossing just the polarized the monitor light and nothing else. And the other one is crossing with all the light coming out. And so it looks dark. So this is fun. And this is the technology behind buying Polaroid sunglasses for you to go to the beach. So if you go to the beach and you wear these glasses, the nice thing is that light reflects off of bright, shiny objects like the sand and the ocean is polarized one way. So let's say that the light is polarized. It's easier for me to hold it like this, just like this monitor, where when this is vertical, it's blocking the rays of light. And so here you are wearing your goggles, or maybe you're wearing them like this so you look better. Well, great. And this works beautifully. You could actually put these over your face like this and wear your mask. Go down to the beach, and people will say, "Oh, look at that. They're protecting their eyes from the glare of the sun." But what happens when you wear your sunglasses while you lie down? Well, when you lie down, you rotate these things 90 degrees and voila, they stop working. So there's no point in wearing your. In fact, as I look at my computer monitor screen of the image of myself on the webcam, when I turn it like this, the image disappears. And when I turn it like this, it transmits it and I can actually see the image. So I'm not sure if you can tell that by looking at the image of me looking at the image of myself. But there you have it. So a little tip about how to correctly wear Polaroid sunglasses when you're driving down the road, wear them like this, of course, to block out the glare reflecting from the car in front of you. When you go to the beach, don't bother wearing them when you're lying on the sand sideways. Another application for this deals with birefringence. And so I thought I would just mention that. It's not anything I really expect you to learn about, but I happen to have a sample of some plexiglass, some acrylic that I laser cut as part of my astrophotography tracking platform project. Ha! This is this was one of the props being displayed during astronomy night during one of the presentations. And it mentioned that, by the way, you can study birefringence if you have a pair of polarizers and analyzers. And I happen to have them. So let's make an attempt at, first of all, what you're looking at is the camera projecting down onto the piece of paper that has the polarizer. And when you look at it this way, of course, you don't see anything. And when you look at it this way, it's really hard to tell what's going on. So let's ignore that. Instead, we already know that this monitor has polarized light coming out of it. And this is a piece of plastic which, in principle, could almost be invisible. If I wasn't moving it around, you'd have a hard time telling that it's there. I know I should bring the webcam closer. But what I'm going to do now is take this polarizer and move it in front of this and see that there's almost no chance that you can tell what's going on. So this is a poor experiment this way. But turns out I have a little piece of technology to try to help me illustrate birefringence to you. And if I can do it without breaking anything, haha, this is a light box. So, a light box is used by photographers to study photo negatives. I'm going to shut off the overhead camera. And so, and what you can see here is that I have this light box. I can take this polarizer, and if I set it just right on the light box, then the overhead camera, which in principle I could focus, is now looking at this, and you're looking at the projection of the light through the polarizer captured by the camera. Excellent. So what I'm going to do is, again, just demonstrate. So if I take the second polarizer, now called an analyzer, hold it directly over the first one is polarizing the unpolarized fluorescent light coming out of the light box. And so it's oriented all one way. The second polarizer, thanks to these handles being lined up by the professor who built this, is also lined up the same way. So you're seeing no more reduction than when it's just one of these. It's actually blocking half the light right now. So hard to tell, but this is full strength light off to the side, which I guess you can just see here with my finger. And then this is half the light coming through this polarizer. I put the analyzer in front of it, and it's still letting that half of the light that made it through the first one to go through the second one. I rotate this, and when we get to that angle of 90 degrees, yeah, you're saying it's not working very well. Okay, so it almost looks like this is circularly polarized light. The point is, I have to rotate it, and it blocks the light. When I rotate it back, it lets it through. Now, the trick of birefringence is if I put certain materials in between, plastic comes to mind, um, maybe magic tape, plastic tape. You can try taking a couple of strips of plastic tape, putting it down on a surface, and then seeing if you can get colors to show up, birefringent colors. So I'm going to take the structure, which is laser cut, and lay it over the polarizer. And so, of course, one problem with that is it doesn't want to just sit there, does it? So I have to build a little holder for it in real time. Yeah, okay. So you're looking through the plastic, through the polarizer at the light source. And now I'm going to take the analyzer, and when I move it around, I could possibly even zoom in on this for you and shift this to where you can see it. So here's a portion of the acrylic, and when I move this analyzer over it, it's now showing, this actually shows up as blue here. It's showing stress points in the material where it was laser cut. Okay, so as I rotate this analyzer around, I'm able to study how stress and strain is present in what appears to be a clear piece of plastic. Okay, so that's birefringence, one of the side effects of polarization. So what's going on is where the stress takes place, it slightly changes the orientation of the polarized light going through it, and therefore it changes its brightness relative to the surrounding background. This concludes my short little overview of polarization of light. There's much more I wanted you to learn in waves, but at least here's one little section. All right, so that's it for now. Ta-ta.